In this lecture, we are going to finally form the equation which represents a generic reinforcement learning problem, and from this we can derive a solution. Let's begin by discussing expected values. By the way, if you've never taken a probability course, then you've probably never heard of expected values. In which case, if you want to understand this, you'll want to take a course in probability. To think about it simply, the expected value is just the mean. So for example, suppose I've measured the heights of 1,000 students, and I want to model this as a Gaussian distribution. I find that the average height is 70 inches, with a standard deviation of 4 inches. In this case, the mean of the distribution is 70, and thus the expected value is 70. Let's look at a coin as the next example. A coin has a binary outcome. If I flip a coin, I may get 1 or I may get 0. Suppose the probability of both 1 and 0 is 50%. In this case, what's the expected value? Well, since it's the mean, that means the expected value is 0.5. Sometimes this terminology confuses people. They ask, how can the value I expect to get be 0.5 if the result can only be 0 or 1? It's important to realize the expected value, despite its name, is not the value you expect to get. So if I flip a coin, I don't actually expect to see the value 0.5. The expected value actually has a precise meaning for both continuous and discrete distributions. Although for most of this section we will assume that we are working with discrete distributions. The idea is that the expected value is a weighted sum of all the possible values of a random variable, where the weights are the probabilities of those values. As a simple example, we can return to our coin example. If we have a biased coin so that the probability of heads is 0.6, then the expected value becomes 0.6 times 1 plus 0.4 times 0, which is 0.6. Because the probability of 1 is now a little higher than the probability of 0, the expected value also becomes a little higher. Alright, so what's the significance of expected values? Well, let's remember that our reward, and hence also our return, which is the sum of rewards, are random variables. At a high level, what this means is that if I play a game 100 times using the same policy in the same environment, I will get different rewards. This is because both the environment dynamics and my policy are probabilistic. And thus, it makes sense to not think about a single return by itself, but the expected value of the return. I would like to maximize the sum of future rewards, but because the result is probabilistic, what I really want to do is maximize the expected sum of future rewards. The expected sum of future rewards has a special name in reinforcement learning. We call it the value function. I always mention that this is a very unfortunate name because the word value is such a generic word. Nonetheless, this is what it is called. Because the return is the sum of future rewards after we have arrived in some state, so too is the value function. As you can see, it's not just a plain expected value, but rather it's conditioned on the fact that we arrived in the state S at time t. Thus, we denote this as V of S, the value of the state S. As a side note, we sometimes refer to the return as simply the reward, even though the return should be a sum of rewards. So you always have to pay attention to the context. As you recall, I said that one of the most important things about the return is that it can be defined recursively. The return at time t, g of t, is equal to the reward at time t plus 1 plus gamma times the return at time t plus 1. And because of this, we can also define the value function recursively. V of s is the expected value of the reward at time t plus gamma times v of s prime, the value at the next state s prime. Now you must be wondering, what is the purpose of all this? Are we just defining equations for the sake of it? Of course the answer is no. Just keep in mind the high-level picture. We are setting up a problem from which we can find a solution. In order to find a solution, we must have a problem. And thus, our job right now is to continue building up the problem so that it is well defined. The next step is to remember that the expected value is really just the weighted sum, where the weights are the probabilities. So if we write it out in full, this is what we get. This is the sum over all possible actions A, and the sum over all possible next states S prime, and the sum over all possible rewards R. Inside the sum, we have the probability of performing action A, given that we are in state S, multiplied by the probability of landing in the next state S prime and receiving the reward R. And then this is multiplied by the reward R plus gamma times V of S prime. In other words, it's R plus gamma times V of S prime, multiplied by the probability of actually getting the reward R and arriving in the state S prime. In other words, the expected value of the return. This is called the Bellman equation. It is the centerpiece of all the subsequent solutions to reinforcement learning that we will discuss. It's worth thinking about the Bellman equation a little more. Notice that, in order to come up with this equation, we only use the rules of mathematics, the rules of probability. It seems like just a regular old expected value. However, the implications are deep. It's interesting to consider that the two probabilities here, pi of A given S and P of S prime and R given S and A, come from totally different physical processes. Pi is our policy and it represents our agent, so you can think of that as like an animal. The state transition probability represents our environment, so you can think of that as the world. So it's interesting that while we can freely manipulate this equation mathematically, these two objects are actually completely distinct physically. At this point, you must be extremely tired. All we are doing is making our formulas progressively more complicated with no end in sight. But in fact, this is exactly where we want to be. Although this may seem complicated, I will demonstrate to you that in fact what we have arrived at is pretty simple. We can now define the first problem in reinforcement learning, from which we can find a solution. Remember that, in a reinforcement learning problem, you can have multiple policies. Some may be good, but some may be bad. How can we tell what is a good policy and what is a bad policy? Well, how about the value function? In other words, if I can find the value function for a given policy, that tells me how good that policy is. We call V subscript pi of S the value function given the policy pi. We call the problem of finding the value function given a policy the prediction problem. As promised, I said that we've arrived at something pretty simple. Let's look at the Bellman equation again. These probabilities are a little deceptive. They have complicated symbols, but they are not complicated. Remember that the policy pi is just a function which we implement in our own code. We know this probability. Therefore, it's not a problem. How about the state transition probability? Let's assume this is known as well. This is entirely possible. Take, for example, the grid world environment. Now, what happens if we know these two probabilities? Surprisingly, this just becomes a system of linear equations, which you know how to solve from high school algebra. Suppose we have three states. Then, if we simplify the summation from the Bellman equation, we would arrive at something like this. So here, the b's and the c's are just constants which are derived from the probabilities, which we've assumed that we know. From this, we can call a simple function like np.linouts.solve, and this would tell us v of s1, v of s2, and v of s3. In other words, if we know both our policy and the environment dynamics, we can solve for the value function using only linear algebra.